It's on that side. So we are going to start this thing. Kepler's problem. So Kepler's problem you might have studied. The context was in your earlier classes. है ना? Three laws of Kepler: first law, second law, third law, which was part of that the time period. Now what we are going to see, we have to study this Kepler's problem in our the way we studied central shabash fields. या हमारा जो last class we just had motion in a central field. So what was motion in a central field? हमने कहा था कि there was a bounded motion and there was unbounded motion. So particles come from infinity, ठीक है? They just in a field. It will take time. It will take time. You have to read it twice, thrice, particularly from this book. Then it will slowly settle down. So the point I want to emphasize that we were, in case of bounded motion, we had only a particular potential, 1 by r and 1 by r. These two examples only construe for us bounded motion. So rest of the motions may not be bounded. Particles may come from infinity and they can again go to infinity, or they can come from the particle near that field and then they could go to infinity, the particular figures. But it's only in particular these two cases we say that the motion is bounded, and उसका एक condition था हमारे पास alpha is equal to 2mn by p, where n and p are integers. One is the ratio of the revolutions. So only in particular cases we had bounded motions. Okay. So these bounded motions become for us interesting. Why they become interesting? Whether it's Earth-Moon problem, Sun-Earth problem, or electron-proton problem, they are going to follow this sort of the thing. Motion in a bounded problem, in a central field. And there was particular reason. अगर हम ये electron या Earth, it's moving in a bounded, why doesn't it exactly coalesce to the center? If it's attracting it so much, why doesn't it come? And so there was a reason. आपने देखा इस book में. So it's a bit you have to just think over it. Why it doesn't exactly coalesce to the center. So if that is, so हमारे पास जो potential form है, इसका form है this alpha by r. And if you remember, U effective was basically, हमने कहा था there was this term plus centrifugal term, which we call as effective potential. Together, these two terms construe for us the potential energy. So as r goes to 0, so as r goes to 0, so this will go to shabash. As r goes to 0, it will go to infinite. Or if r goes to infinite, it will go to 0. So at two cases, the value of potential or the value of potential energy in the given field is dependent upon this value of this dependence on r. This depends on r in a given field, such that it can be infinite, it can go from plus infinity to minus infinity, depends. It goes to r 0 plus, or r it is coming from minus infinity to 0 or plus infinity to 0. So you can have both of the signs. Effective because once we took recourse to this coordinate system. U effective हमने लिया ना, we take why, that's why we are going to use Lagrangian. हमने क्यों use किया basically? So we take different coordinate systems. Different coordinate systems. So we have a v is equal to if it's simply radial velocity, it's dr by. But since it is v is equal to r, so it's r d theta 2 minus theta 1 by dt. It's the angle, how the particle is changing the angular velocity. At any point, its angle is changing. So it can have also radial component. So at a given point, a particle can oscillate. It can move radially, okay? Or it can move in a field. The question is which component we are interested in. So if we are interested in radial, so r theta, we can have all three coordinates. R vector, theta vector, whichever coordinates is relevant to understand which way particle is moving. It's moving laterally, it's moving horizontally, it's moving vertically. So if you take recourse to simple coordinates, we have simply x and y. हम इसको ऐसे कह सकते हैं, r cos theta, y sin theta. But चूंकि we are taking recourse to, हमने इसको define किया था, we defined it in terms of this elliptical, this coordinate system, or coordinate system was like this. Energy को हमने ऐसे define किया था, r square phi dot square. तो हमारे पास एक r dot square भी है. अब वो ये क्या setting a Lagrangian means what? Setting a Lagrangian means we have to set Lagrangian in a way the coordinates which you can ignore. For example, if the particle is moving in a central field, so phi dependence is constant, so you can ignore those coordinates. इन्हीं को कहते हैं cyclic coordinates. So the main reason of going from classical way we define classical mechanics to Lagrangian dynamics is how we can choose those coordinates. Those are known as generalized coordinates. And how we can sometimes reduce the ignorable coordinates or cyclic coordinates, जो हमारी differential equation है, Lagrangian equation of motion, how it will become simplified depending upon the particular system we are interested in. ठीक है? So it may not have one simple, जो आप कहते हैं ये term नहीं है. Since we have defined things this way, तो phi dot को हमने फिर ऐसे in terms of angular momentum define किया. And हमने define किया था, we had defined, if you remember, we defined phi को हाँ, m is equal to mr square phi dot, है ना? Phi dot is equal to m by mr square, है ना यहाँ पर. So that's it, from this term plus this term, इसको हमने क्लब किया, that's why we got this extra term. Got my point? आपको क्वेश्चन, हाँ, इधर you got my point where from we got this extra term. We got this extra term because we had a different coordinate system. In that coordinate system, we not only had r dot, we had r dot phi dot square. And phi dot को हमने in terms of angular momentum ऐसे भी define करते हैं. So we got 3 terms, not 2 terms. The extra term, जिसको हम centrifugal term भी कहते हैं, we clubbed it together. That's the way we got it, U effective. ठीक है? So if it is that way, for example, so we can also sometimes, if we define R in terms of, अब यह है कि the value of this can be minus and plus. Normally potential का value minus होता है ना? U is equal to minus 1 by R. Why? du by du R आएगा ना, ये plus आएगा फिर. That will give us force, है ना? So potential moves in the opposite direction quantitatively. ठीक है? अब वहाँ से आ रहा है तो you have to field will work on the particle. If you take the particle away from the field, you have to do work against the field. ठीक है? So these are the, so here this plus minus depends upon whether it's going against the field. We are calculating the quantity in the direction of field or against the field. So we can have this plus minus value can get flipped accordingly. ठीक है? That's the point. तो अगेन अगर हमारे पास इफ यू टेक और अगेन इफ यू डिफाइन और इन टर्म्स ऑफ यहां पर है ना, और अगेन यू डिफाइन इट इन टर्म्स ऑफ एम स्क्वायर बाई एम अल्फा, if you define R this way, then U effective or U minimum can also be if we if you अगर हम इसको what we are going to do, if you want to इस R को हम fundamentally we are और U effective की explicit dependence on R we are going to fundamentally change, then we define और को हम ऐसे डिफाइन करेंगे ओनली इन टर्म्स ऑफ दिस m and alpha is the reduced mass. So then you can also have U effective as like this. So here we have not necessarily take to course this thing whether R goes to infinity or R goes to zero. दो केसेस में, एक्सट्रीम केसेस में यू कैन डिफाइन थिंग्स इन ए जनरल वे. अगर आप पिक्टोरियली यू वांट टू हैव अ पर्टिकुलर वे हाउ द डिपेंडेंस ऑफ R vis-a-vis U effective, it will come out to be like this, है ना. तो अगर ये जीरो है ना, जीरो, सो इट विल गो जीरो से ऊपर या जीरो से माइनस, बिकॉज अगर ये एग्जैक्टली वी वुड नॉट हैव गॉट दिस टर्म, तो द पार्टिकल वुड हैव स्टार्टेड फ्रॉम द ओरिजिन. ये है ना दिस एक्स्ट्रा टर्म, एंड दिस मीन्स द पार्टिकल विल स्लोली एंड ग्रेजुअली गो टू इंफिनिटी. मतलब इट मे कम फ्रॉम इंफिनिटी और इट विल go to infinity. It depends upon whether R is 0 or R is infinity. If R is infinity, it will gradually come to some stable minimum. है ना? So since if it is 0, then that stable minimum can be origin. ठीक है? Now the point which I want to emphasize is that we have to study bounded motion. ठीक है? Which is a particular case dependent on हमारे पास दो potentials हैं, एक 1 by r square है and 1 by r. So 1 by r we'll do in the later, इस बुक में एग्जाम्पल है उसकी 1 by r की. So we are this time concentrating on 1 by r square. उसी को हम in your earlier classes आप इसी को Kepler problem भी करते हैं, है ना. अब before I am going to start Kepler problem, I'll just उसके लिए I will थोड़ा सा एक सजेशन नहीं, एक एक्सरसाइज विच यू हैव टू डू एज अ मस्ट, अदरवाइज यू नॉट अंडरस्टैंड दिस. एक्सरसाइज ये है कि यू हैव टू रिहैश योर जो आपका कॉनिक्स है ना, कॉनिक सेक्शन, सेक्शन जो भी आपने पढ़ा है ना, यू रिहैश इट वेरी वेल. व्हाट इज डायसेट्रिक्स, व्हाट इज फोकल लेंथ, व्हाट इज eccentricity, and the eccentricity will come out to be greater than less than 0, है ना. For different figures, ellipse के लिए क्या आता है, what's for hyperbola, circle के लिए क्या आता है. So general equation of ellipse क्या है? So basically its cone is traversing a trajectory. In some case of trajectory of this 1 by r square, so it will the trajectory is ellipse. And that ellipse is as if a particle is moving in a bounded system, a two-body system. A particle को कोई field होगा, उसके around move करेगी. So the particle की trajectory, geometrical trajectory of the particle has to be seen. So अब हमारे पास क्या है? हमारे पास है, we already know, if you remember in the last class, हमारे पास equation थी in the form of t and in the form of phi, है ना? If you remember, we had an equation in the form of T and phi. T was कि पार्टिकल कहां से कहां पे जाता है, क्योंकि हमारे पास और पैरामीटर नहीं था. द पार्टिकल इज नॉट मूविंग रेडियली, हमारे पास पैरामीटर है phi, है ना. ये ऑर्बिट यहां पर है, जैसे अर्थ है, अर्थ सन के अराउंड, या मून है ना, ये मूव करता है ना, 27 दिन में एक होता है पूरा 1 month. तो चलो वो हो गया स्पिन अराउंड, स्पिनिंग अराउंड. चलो विल टेक इट, इसका रेवोल्यूशन, अर्थ का रेवोल्यूशन अराउंड सन, दैट इज 365 डेज, है ना. बट इसका मोशन हो रहा है ना, phi का वैल्यू चेंज होता है एट डिफरेंट पॉइंट्स. समटाइम्स इफ इट्स फॉलोइंग द मोशन ऑफ एन एलिप्स, समटाइम्स इट्स क्लोजर टू सन एंड समटाइम्स इट्स far away from the sun, है ना, उसी को हम apogee भी कहते हैं, we call it something a closer distance, it's called apogee, and the farthest distance को, हाँ, ठीक है, हाँ. So we have to study these things. So my this thing is that जो conic section है, again you see it, different dissects किसको कहते हैं, ellipse किसको कहते हैं, hyperbole, ठीक है. So knowing that जो हमारी थी, since the particle is moving in a bounded motion, तो हमारे पास दो equations of motion है, एक t है, एक phi है ना, which we solved in the previous class. And knowing the value of t and phi, knowledge of that phi, we are going to calculate the trajectory of the particle in the bounded system, which follows this 1 by r square potential. So this is our exercise. You got my point? This is our stage, what we are going to do. And this is called in literature, इसी को हम Kepler's problem भी famously कहते हैं. Kepler's problem you have studied in your earlier classes. 3 laws, the time period of this is going to square of this and cube of this, है ना, वो जो भी है. Equal areas, take equal time. And 3 laws. So उसी को basically the knowledge of equations of motion and knowledge of conics. This we should we are going to do it as an exercise. ठीक है? This is what we are going to exercise. So if you remember, these equations which were very much important. Actually, the equation was like this, dr by dt, है ना, जो हमने सॉल्व किया था, तो उससे हमने t निकाला था, इसको, so t came out to be like this, 2 by m e minus u plus constant. This is time and this is phi. So knowing these two equations, एक हमारा दे रहा है कि टाइम पीरियड कहाँ से कहाँ तक है. For example, the way you calculate in your earlier classes है velocity of particle at time t. Equation of motion है ना 5 मिनट के बाद क्या है, at time t is equal to 5 seconds. तो it is 5. These two differential equations are there. ठीक है. Now we have to solve them vis-a-vis this 1 by r square potential, है ना, 1 by r square. That should give us Kepler's problem. हाँ, अब ये है कि here this phi है ना, phi we are going to do, ये है m dr by r square divided by 2 e minus, so now you are going to substitute here u is the value of potential. तो u कैसे वैरी कर रहा है, शाबाश. It varies in our जो हमारा ये तो it varies like this for bounded mass alpha by r के हिसाब से वैल्यू कर रहा है पोटेंशियल. So we are going to substitute u here. ठीक है. So if we are going to substitute u here, so it will be alpha by r minus m by r square. अब यह है कि it may come out in minus plus. It depends upon whether it's minus or plus, both cases. If it's coming closer to the center of mass or it's moving away from the center of mass. So अगर ये है, now you have to see it in terms of basically differential equation है ना, ये basically it was phi 2 minus phi 1, phi 1 phi 2. ठीक है. Now you are going to solve this integral. So this is a sort of homework problem actually. I'll just, so the book has straight away gone from this to this, ठीक है. So if you do good, ये हमारा मकसद नहीं है solve करना integral, but you have to convince yourself unless you are able to solve it. एक दो रफ के page and see. So how this value of this integral कैसे आएगा, ठीक है. So the value of integral comes out to be अगर if you have, it will come out to be pi inverse phi, या it will come in terms of cos phi की फॉर्म में इसको आप सॉल्व करोगे. सो फाई का वैल्यू आएगा, ये cos phi आएगा, फिर phi आएगा cos ऑफ इनवर्स समथिंग, cos इनवर्स m by r minus m alpha by m plus constant. So we will do this here, but it will take our full class. Then, so if you don't do it, अगर आपको नहीं निकलेगा, ठीक है, I'm here. So you try to see. You have to simply, the way you will do class, you have solved integrals of different kind. So you solve this integral in terms of phi, its solution will be like this in terms of phi. In terms of phi. Now what we are going to do is we are going to take origin of phi such that constant is 0. So if it starts from origin and putting p का value हम लेंगे, p लेंगे, ये है ना p, we're again going to have some changes. p को हम define करेंगे ऐसे, we define p as m square by m alpha. ये है ना हमारे पास, we got this equation in terms of this. We are going to somehow define p in terms of m by m alpha. And e को हम define करेंगे in terms of eccentricity. Basically ये phi है ना, ये cos phi is basically angle. It's ratio of base है, जो भी है, ठीक है. अब वो है. So we are going to see how our knowledge of conics, and we are going to reparameterize coordinates. P को हम define करेंगे ऐसे, and E को हम define करेंगे like this. One plus so what, how he has defined इसको आप देखो, यहाँ आप निकालो 2me है ना, ये m square, ये LCM है ना, इसको m square, it will be multiplied by m square, फिर 2em square by m square को बाहर निकालो, अंदर निकलेगा 1 plus this divided by this, and उस सब को हमने in terms of e define किया है. So ये थोड़ा सा simplify करके we define things, इसको हमने in terms of p define किया and इसको हमने डिफाइन किया इन टर्म्स ऑफ E. E इज नॉर्मली इसेंट्रिसिटी. इसेंट्रिसिटी कैसे हम डिफाइन करते हैं? इट्स द रेशियो ऑफ दिस सेमी मेजर एंड सेमी माइनर एक्सिस, है ना, विच विल कम आउट बी 1 फॉर दिस ऑफ सर्कल, लेस देन 1 फॉर हाइपरबोला, ग्रेटर देन 1 फॉर पैराबोला. ऐसा ही ना, समथिंग लाइक दैट. And 2p is called the lattice rectum. And E is called the eccentricity, which you might have studied, but again you need to rehash it. And phi is equal to 0. ये आप origin भी लिख सकते हैं. Normally we take it as a point nearest to the origin. उसी को हम perihelion भी कहेंगे. So we normally take it as origin, but we take it as a point closer to origin. उसी को हम perihelion भी कहते हैं, है ना. And the point away from far away, उसी को हम कहते हैं perihelion, हाँ, ephelion. It's called ephelion. Yeah, you're right. So. और उसको कहते हैं अपोजी और पेरिगी, पेरिगी है ना। दीज आर डिफरेंट वो जो वेज ऑफ सेइंग द सेम थिंग। सो अब ये है कि टू पार्टिकल्स interacting according to law of 15.1, according to this law, two particles if they are interacting according to ये वाला potential 1 by alpha by r, और ये interact ऐसे कर रहे हैं, and so the orbit of each particle in conic section with one focus at the center of mass of two particles, at the center of mass है ना, दो particles की ये है, two particles are moving, ठीक है, एक नॉर्मली ऐसे मूव कर रहा है ना, दिस इज अ बाउंड सिस्टम, ठीक है। अब जब सेंटर पे पार्टिकल होता है नॉर्मली से इसका फील्ड होता है, ठीक है, जिसकी वजह से द अदर पार्टिकल इज गोइंग टू जस्ट कम क्लोजर टू और इट विल मूव अगेंस्ट इट। अगर रिपल्सिव इंटरेक्शन होगा कूलम्बिक इंटरेक्शन में इट विल गो अगेन, और ये होगा अट्रैक्टिव इन केस ऑफ ग्रेविटेशन इट विल, so they will form a bound system. So the bound system will correspond to trajectory of particles which will be described differently, depends. हम ये जो है रेशियो P and E क्या आएगा, it will be different for different trajectories. तो जब ये क्लोजर होगा एपीजी एंड पेरोजी का जो रेशियो होगा वो क्या, इसेंट्रिसिटी, तो उसी हिसाब से पार्टिकल की ट्रेजेक्टरी पैराबोलिक भी हो सकती है, हाइपरबोलिक भी हो सकती है, इलिप्टिकल भी हो सकती है, या सर्कुलर भी हो सकती है, ठीक है। ऑल द फोर केसेस में बी देयर, ठीक है। दिस इज द थिंग। सो वी हैव जस्ट सॉल्व दिस इक्वेशन, सो दिस इज द थिंग। सो फॉर एग्जांपल अगर हम इफ यू गो टेक रिकोर्स टू नॉर्मल, इस सब्जेक्ट किसमें वे डू यू स्टडी, इस सब्जेक्ट को क्या कहते हैं, व्हेन वी एसोसिएट अ नंबर विद अ पॉइंट इन स्पेस, शाबाश, when you associate a particular number with a point in space, geometry subject of, इसको कहते हैं analytical geometry, analytical geometry। ये हुई कार्टेशियन ज्योमेट्री, एनालिटिकल ज्योमेट्री है ना। तो द सब्जेक्ट ऑफ एनालिटिकल ज्योमेट्री है, इसका ये है, उसको क्या कहते हैं, बेस, इंग्रेडिएंट, स्टेज है ना। पार्टिकल मूव करते हैं ना स्पेस में, ठीक है, तो स्पेस में वी नॉर्मली टॉक ऑफ पॉइंट्स की ट्रेजेक्टरी इन स्पेस, सो वह टू रिप्लेस नो पॉइंट्स आर नॉट इन स्पेस वेयर द पार्टिकल्स आर मूविंग इन द स्पेस, सो इट्स नॉट ट्रेजेक्टरी ऑफ पॉइंट्स, इट्स ट्रेजेक्टरी ऑफ particles in the space, that's the point. So if it is for example, अब ये हमारे पास ये है केस ये है, for example if E is less than 0, so equation जो हमने डिफाइन किया था E यहाँ पर ये है ना, E is the energy of the total energy of the particles, ठीक है। अब ये है ये क्या आएगा, प्लस आएगा, अगर ज्यादा होगा कम होगा, ये डिनोमिनेटर में है ना ये, तो क्या आएगा, 1 प्लस माइनस आएगा या क्या आएगा, जो भी है। सो इफ E is less than 0, if E is less than 0, then eccentricity is less than 1, कैसे है ना, कुदरती आएगा ना लेस देन 1, अगर लेस देन 0 आएगा, ये 1 माइनस समथिंग इज लेस देन 1, उसका रूट आएगा, इट विल बी नेचुरली लेस देन 1। अब इसमें आपको ये सिर्फ कन्विंस करना है, मैंने डिफाइन cos फाई है ना, फाई का वो आएगा ना ऊपर वाला cos, सो व्हाई शुड वी डिफाइन दिस E इन टर्म्स ऑफ दिस, ठीक है। दिस इज ये आप इस पर यू जस्ट थिंक ओवर इट। So if you define eccentricity, if E is less than this, if this is less than 1, so it will correspond to the orbit of an ellipse. So if you go to the your textbooks in this conic section, you will see how we define elliptical condition क्या है. Elliptic condition है when eccentricity is less than 1, which will correspond to when the energy, total energy of the system, bounded system, 1 by 2 r square phi dot square plus जो भी है 3 terms हैं, that will be less than 1. ठीक है, if it corresponds to this thing, it will give us motion of an ellipse. So अगर हम if we have a diagrammatic so इसमें अब हमारे पास आते हैं ना, 2 रेडियस आता है, एक स्मॉलर रेडियस आता है एंड द larger radius. You got my point? So we define it in terms of A and B. So it's 2B, it's A. So यहाँ से यहाँ तक it will be 2A. So एक तो यहाँ से है ये रेडियस और एक यहाँ से है. So यहाँ से यहाँ तक you can see it either it's A और यहाँ से यहाँ है. So semi minor axis है, semi major axis, that's unit. अब ये है कि if we define things in a way we define A as B by 1 minus E square as alpha by root 2, alpha by 2E. So how come आप दिखाओ इसको, how come this A is equivalent to this? So you do nothing, P को substitute करो U, this value, and 1 minus E square you substitute it here. When you थोड़ा सा simplify करो आप, ठीक है, it will take 1-2-3 line. After simplification, or you can do here also, but you have to simply simplify it. So A will define it in terms of this. So A can come out to be this. A is the one of the radii of the semi-major axis. And इसी तरह हमको B भी define करेंगे, ठीक है. फिर हम जो trajectory of particle है in terms of R minima and R maxima करेंगे. So when the particle is closest to the, जैसे हम कहते हैं ना seasons कैसे फॉर्म होते हैं, कैसे सीजन फॉर्म होते हैं, शाबाश है ना. जब मतलब क्लोजर विंटर के टाइम जब क्या होता है, सन अर्थ का होता है, दूर होता है ना, तो इट्स अपोजिट मैक्सिमम है when it's closer. So in the same way you can this is cross. In the same way जो particle की trajectory है when it's focused, when it's closer to it, R maximum आएगा R minimum, तो radius का maximum होगा, ठीक है. So we are going to do these calculations and accordingly see for 1 by R square, ठीक है. That's it. So we are going to take A is going to this. And because we have defined a radii in terms of A and with or not, for example, जो अगर हमारे पास सर्कल होगा उसका radius है simple R. So here radius varies from R max to R minimum. So we have to define R max कब आएगा and R minimum कब आएगा. Then we'll know exactly how things will define the things accordingly. So A is this. Now this is A. In the same way, B will define as P by root of 1 minus E square is M by root of 2M E. So what's the time? So maybe I'll just stop here because we will not complete it. So what I'll stop here. Before stopping, I'll just only state it. From tomorrow we are going to in a detailed way. Yeah, what's the time? So I'm going to write R max. Or you can also write it as A into 1 minus E, है ना? So you can इसको आप ऊपर लोगे, है ना? It will be basically P into 1 plus E inverse. So we'll have some binomial theorem, so you can also write it like this. In the same way, R minimum, ये R minimum आएगा, R maximum आएगा P by 1 minus E. That will be A into 1 minus E. So only one thing is minimum and maximum में ये plus है, ये minus है, ये minus है, ये plus. So with these two knowledge, ये अब हमारा कल का काम क्या है? So I thought it will be today. So what you are going to do at your place, थोड़ा सा you rehash your knowledge of conics. How we define ellipse, parabola, hyperbola, and equation of circle. वो लेते हुए and how we define those eccentricity, disectrix, major axes, minor axes, apogee, perigee, these things should be clear. And इन सब को लेते हुए तो हमारे पास ये इक्वेशन थे, ये वाली इक्वेशन in terms of t and in terms of phi. And we are going to define it for 1 by r square potential, and we have 1 by r square potential which construes for us Kepler's problem. ठीक है, Kepler's problem in a bounded motion. So ये सब information and knowledge लेते हुए we are going to see the details of it tomorrow. ठीक है, stop. आप ये मुझे attendance